All right, so let's see. Video over, I guess, types of bonds, right? I guess that's kind of what this video is about. And so, oh, my computer decided to make a phone noise. Um, Basically, there are two kinds of chemical bonds, okay? And, I'll just use this little paint, old fashioned technology here to kind of walk you through that, all right? And then we'll talk about how to make some predictions, right? That's why we like this. Science likes making predictions. So we have two kinds, okay? And the first kind, I guess I'll change the font size here, is, I guess you would say, most chemical bonds. I mean, not that I have a count in my head, but I think most molecules that I can think of, the high percentage are going to be what are called covalent. Oh, if I can type. Oh, I'm typing up here. That's why. They're called covalent. So let's do that. Covalent bonds. Okay. And when we say covalent, you should be thinking the word co. The prefix co means like with, right? Like if you co-parent, you parent with somebody. If you co-inhabit, you live with somebody, etc. Right? So covalent means like two valence electrons together. Excuse me, still coming off a cold or flu. I don't know which one. One of the fun viruses. But anyway, back to this. Covalent implying that there are two valence electrons being shared. They're together between two atoms, between two elements. Okay, so you really want to think of this as sharing a pair of valence electrons. Okay, so when you talk about a covalent bond, you're thinking about this idea of like if an element has a valence electron, let's say it's fluorine, he has seven, right? So one of his valence electrons is here, and imagine it as when you think of those seven. Maybe before I do the pen, let me maybe draw it. Maybe a little bit easier to visualize, right? That's way too big. So you look at fluorine and you say, okay, here's fluorine, and his Lewis dot diagram looks like this, right? He has seven valence electrons. The reason we draw Lewis dot diagrams like this is partially to account for them, like how many there are, but mainly to think like, oh, there's a spot, right? Like there's missing a valence electron here. Like fluorine will be complete. He would get to behave like neon. He would gain a large amount of neon's stability by having his eight valence electrons. Remember this idea that eight is like the magic number. Okay, it's called the octet rule. And if you're taking physical science, you're probably like, okay, yeah, you said that, but why? The short answer is orbitals, which we don't talk about really freshman year, but you take chemistry your junior year or whenever, then you talk about orbitals. And so the short answer is an s orbital and a p orbital in a period add up to eight valence electrons. Eight electrons can fit in that highest energy level, okay? But that doesn't really matter if you're taking physical science, at least for me. I mean, maybe for another class it would. I'd love to teach about that, but I got to make sure it's grade appropriate, right? Consistent with what the expectation is for a freshman versus, say, a junior. Okay. But anyway, you say, okay, eight electrons, great, got it. Think of it as this spot here is missing an electron. So I want you to picture back to this pen example that like that is the single electron. It's this electron here. So fluorine's got this guy, and he would love to have an eighth one. He would love to pair it, if that makes sense, complete it. Okay, technically he's filling his 2p orbital, his 2pz orbital that wants to be filled. But that's, again, you don't need to know that for this class, at least not for physical science. If you're taking chemistry, then you're like, oh, okay, yeah, I remember that. Anyway, moral of the story is he's got this one. He's like, I want to find another one. He has a spot here. He would love to find another electron. So imagine another fluorine comes by, okay? Because there can be obviously more than one atom. And that other fluorine's over here, and he also has his seven valence electrons. Notice I drew it like this time. It's perfectly fine as long as I have my three pairs and my one single, okay? You can't do like, well, for fluorine, there's only one way to do it, right? 2, 2, 2, 1. Where the 1 is doesn't matter. Okay, usually we do clockwise, starting from the top, but it really doesn't matter that much. Okay, as long as you have the pairs when there's pairs and singles when there's singles. Okay, it matters a lot more if it's like nitrogen or oxygen, because then you have to make sure two pairs, two singles for oxygen, one pair, three singles for nitrogen, for example. And we'll get to that in a minute. So anyway, I want you to picture that, like, one fluorine has this pen, the other fluorine has, I don't know, this is their electron. And what basically happens is they both try to steal from each other, okay? The fluorine's nucleus, right, is like, ooh, an electron, and tries, let me change colors, it tries to grab one of the electrons. We're going to make it simple and say it's that electron, just to make things simple, right? So he says, ooh, an electron. He tries to grab it, okay? And meanwhile, as he's getting close, and again, don't they're atoms. They don't have minds. They don't have plans, right? But when they get close to each other, think of it as it's like they can reach out and grab that electron. Okay? Again, it's an analogy. It's not perfect, but hopefully it helps you understand. So while this fluorine's reaching out, this fluorine does the exact same thing. It says, ooh, an electron, right? They both want electrons. They have high electronegativity. So they reach out and try to grab each other. So basically what's happening is this electron, this is one fluorine, this is the other fluorine, basically grabs and tries to pull it. Meanwhile, this fluorine tries to grab and pull this. So they're basically locked in, holding on now to how many valence electrons? 2. And because they're, I just broke this. That doesn't happen. They don't break electrons. So let's back up here a second. They're both pulling. And it's like tug of war, and no one's going to win. And that's a bond. They're now kind of stuck together. Okay, they would love to just take the electrons themselves, but they're not strong enough. So what happens? They're just holding on forever. And that makes a bond. Okay, now if you look at this, it gets a little messy. So let's maybe just draw, I guess let me go back here, right? If I draw this back out, draw that back out here. I want you to picture that basically what happens is you can visualize that as they both reach out and try to grab those electrons. This isn't too bad to look at, but it gets a little messy. So what we often do is we take these Lewis dot diagrams, and once we figure out like where the bond is and how many bonds, we turn into what's called a Lewis structure, which is basically the same thing, a little bit neater though. So what does it look like? You probably noticed that these are 2 fluorines bonded together covalently. They're sharing those electrons. So we would draw it like this. I'd have F, and then I'd have a line to the other F. Okay, and that line is the same thing. Okay, this line here is the same thing as those 2 electrons being shared. Okay, so just neater to look at. It's just a little bit easier, right? And then one thing to not forget, if you're a freshman, I won't make a huge deal about this, but if you're a junior, you better believe, or that is to say, if you're in chemistry, you better believe I'll make a big deal about it, is that there are still electrons left, right? So yeah, these 2 electrons are accounted for. They're in the middle, if it makes sense. Okay, but there are still these these are what are called I should say they're called lone pairs. Okay, technically, but these are unreacted electrons, right? These electrons are still hanging out, right? They're still in fluorine. These are still the other 6 valence electrons. Okay. And that matters a lot. It's not just, we don't just put dots to waste space or whatever. There's a reason for it. Again, if you're a freshman, it's not, for what we do with it, it's not a huge deal. But if you're taking chemistry, it's a very big deal. It'll matter a ton when we get to molecular geometry. So my advice to you is make sure you include it. Okay, and if you're a freshman, it doesn't hurt to include it, right? Like, why leave it out? I guess if you forget, it's not the end of the world, is what I'm trying to say. But if you're a junior, it's a big deal. Don't forget. So anyway, this is fluorine. This is F2. Okay, the formula would be, if I can draw, I'm getting a writing tablet to hopefully make this easier in the future, would be F2. Okay, 2 fluorines bonded together. It's covalent because it's being shared. You might say, how do I know it's covalent? The short answer, so if you're a freshman, the short answer is these happen between nonmetals, okay? Which simply means this. If you're on the right side of the periodic table, so let's do this. I guess we'll go here, right? If I go to, what am I looking for? Oh, yeah, P table. Yeah, that's right. If I'm looking at the right side of the periodic table, okay, these are nonmetals, all right? And if they bond, with a couple of exceptions. I mean, I don't want to get too much into like, what about this? Because there are like some nitty-gritty ones where it makes sense, but I don't want to get into that. Not because I'm not saying it's not interesting. I'm just saying you're learning this, especially if you're a freshman. I don't want to scare you from chemistry, okay? But basically, these are all nonmetals. And basically what's happening here is like if sulfur reacts with oxygen, okay, that's going to be a covalent bond, 100%, okay? If silicon reacts with chlorine, that is going to be a covalent bond, right? Now, if aluminum bonds with fluorine, that's going to be more thought of as an ionic bond, okay? So there are exceptions. But my point is, if it's anybody way over here on the right side, you should be thinking covalent bond. If it's somebody on the left side reacting, okay, the metals, especially if it's an alkali metal, or if it's an alkaline earth metal, especially if it's those, you're going to be thinking, oh, it's probably ionic, not covalent. Okay, and it gets messy. If you really want to, and if you're a junior, we'll have a video over this specifically. Um, but I might as well just mention it right now. If we go in and we look at how do you make this determination, just in case you're wondering, you might say, is it really just where it is on the table? It's not literally being more left or more right. It's the fact. I'm just looking for where to go. Here it is. Not electron. Well, electron affinity would also likely work, but what's called electronegativity, which is basically is the key word. How hard does an atom pull on electrons in a bond? Okay. So you can see fluorine is the king. Fluorine is insanely electronegative on the Pauling scale. Okay, whereas francium and cesium are weak. They do not want electrons, and this should comport to what you've learned already. You should be saying, oh yeah. The metals, they don't want to gain electrons. They want to lose electrons. Exactly, because they have low electronegativity. Okay, and then the nonmetals correspondingly have high electronegativity. They want to gain electrons. You might say, hey, how come like these don't? That's because they don't form compounds ever. Okay, there are no compounds of neon, there are no compounds of helium, there are no compounds of argon. Krypton and xenon, and radon as well, but I guess they just don't have data on it, will form compounds. It's hard, it's not easy. they don't want to share their electrons. But if somebody like fluorine comes in, they're going to have to share electrons, unfortunately. Okay, their nuclear pole is not strong enough. There's too much shielding to prevent that. But again, this is just in case you like chemistry and you're like, wow, that's really cool. Okay, if you're like, I don't really know what's going on, that's okay. I'll have a separate video on this. So anyway, back to our bonds, yes? Okay, so we say happens to be nonmetals, and then we would say technically this is when there is a difference in electronegativity that is sufficiently large. And if I remember correctly, I don't really hold people to this too much. It's when the difference is greater than about 2. Okay, and you say, what does that mean? It means if you look at the periodic table, let's pull that up again, 1 second. If I took fluorine and oxygen, if you subtract those numbers, 3.98 minus 3.44, you get, what is that, 0.54? That's obviously that's not greater than 2. So that's a covalent bond. If I did like boron and fluorine, right, you're like, oh, that's getting kind of close, right? 2.04 and 3.98, and you're pretty close. And some people would call that ionic. And some people would call it covalent. Technically, a lot of times we would say it's covalent. Some people even put the number as 2.2 for the difference. I don't think there's a bright line difference. It's more the behavior of the bond becomes gradually more ionic as the difference gets bigger and bigger and bigger. And at a certain point, we just say, you know what, we're calling it. This is ionic. And if you're like, but come on, it's a word. Doesn't it have meaning? It does, but it's kind of like if I told you where space begins. Believe it or not, there is no accepted space begins this high above the surface of the Earth. Okay, there's different ways you could think of it. There's different ways you could say we're in space now, believe it or not. Okay, so like, it's basically like a, hey, we usually say if the difference is greater than 2. Okay, so then what would be greater than 2, right? If you take any of these bad boys and react them with, say, oxygen, you're going to see, oh, that's instantly ionic, right? If I took any of the alkaline earth metals, same thing. Right, take them, react them with oxygen. You might say, what about beryllium? That's what one. That's almost 2. That one you probably would still call ionic, right? But again, it's kind of getting in that gray area. Okay, the ones in the middle, the transition metals, you might notice they have, not that I'm saying it's high, but they have higher electronegativity than the alkaline metals and the alkaline earth metals. Generally speaking, we're still going to consider them to be ionic when they bond with nonmetals, which, by the way, is pretty much the only way they're going to bond. Okay, there really are no, I'm not saying there's none, but basically metals don't react with metals. Okay, they can ally or make alloys, I should say, together, right? You can like melt them together and mix them, like make bronze, make pewter, make not tin, brass, pewter. What else is well, I guess steel, that's kind of complicated. The point I'm trying to make is you can make alloys, and alloys are basically mixtures of metals. Okay, they look like, oh, that's a metal. It's a mixture. So like brass, right? You play a trumpet or something like that. That's a mixture of what, copper and I think tin. I don't know. It's been a long time. But the point is, those are alloys. Okay, they don't bond though. Okay, they're just mixed together. Okay, but if you notice, some of these metals are, I mean, not that bad when it comes to electronegativity. I mean, you can look at tungsten, 2.36. That's higher than boron, nearly as high as carbon, right? I mean, tungsten, I mean, that could potentially react with like one of these metals, right? But the point I'm trying to make is that we usually are going to think of the ones in the middle as being forming ionic bonds. And again, we'll get to that in a second. Okay. Hopefully this is making sense. Hopefully you're not like, oh my god, he's rambling. I'm trying to explain a lot here. You can of course, like move forward if you're like, okay, he's just rambling about this, but I think it makes sense. Yeah. So basically, what I would say is, especially if you're a freshman, especially if you're in physical science, is any metal and any non-metal is essentially a ionic bond. Okay, and if it's a non-metal and a non-metal, then that's going to be covalent. Okay, that's a simple way. If you're a junior taking chemistry, then you want to be a little more careful. Okay, because I want to have you be more nuanced with your understanding. Okay. Anyway, back to this. So this is pretty good for the covalent bonds. Covalent bonds are, I guess what else is there really to say about them is a bond means now these two things are together, right? If we go back to these fluorines, they're sharing electrons. They don't want to break apart. Does it mean that they're never going to break apart? Does it mean fluorine is just happy? Not necessarily. There's better potential partners for fluorine, if that makes sense, right? Like two fluorine atoms together, like they're happy, but there's better partners. It's like the analogy, what's that meme? I don't remember the name of it, for those who like memes. What is it? Let's see, the guy checking out. Oh, look at that, it knows. Yeah, you know this one, right? I mean, like, this is literally what happens. Like, it's like two fluorines together, and then it sees, like, a lithium, and it's like, oh, my God, it's perfect, okay? It's actually a very good analogy for it, okay? Like, there's stability in that bond, but there could be better options, okay? And that's how chemistry works, is why do reactions happen? The implication is it's better than what it was in. And if it's not better, if you're like, well, then how do you make the things that aren't better? Like, how do you make the unstable stuff? Oh, you need energy, right? Like, you need energy to, you always need energy to break bonds. That's always true, and we'll talk about that. Making a bond always releases energy, but there are bonds that can be made that are just way better, way more stable than other bonds. So if I want to make a crappy bond, like a really weak bond between two things, I can do it, but it's going to take energy to get it to work. Okay, especially if I'm from something that's way better than that. Okay, if you play like Minecraft or something like that, and you're saying, okay, I don't know, what is he talking about? If you get iron ore, you have to like smelt the iron, right? Purify it. That's real life. Like we don't just dig in the ground and find iron that's pure because it's reacted with the air. Because the air is a better, like think of it as it's more stable to make iron oxide than it's just be pure iron. And you want to break those bonds, you want to break apart the oxygen, you need energy because it was happier that way. And you're making it less happy, if that makes sense. Okay, we do it because we need it, but you see what I'm saying here. Okay. So anyway, hopefully this is all making sense. Hopefully you're not going, oh God. Hopefully you're saying, wow, this is cool. Chemistry's fun. I don't know. All right, so covalent bonds, right? And then we have what are called ionic bonds. Ionic bonds. And these are different. Because these, so I guess we'll do this. We could say this is taking / giving electrons. Okay? So instead of sharing, instead of like, hey, I got it, we're holding hands, we got the electrons, we're not going to let go. Now it's like, you have an electron, I want an electron, yoink. And so this guy doesn't have his electron anymore. This guy now has an extra electron. Okay? These bonds are, number one, much stronger than a covalent bond. Much stronger, okay? I think there's a couple of exceptions, like if I had like triple bonded nitrogen, for example, or like acetylene, which is a triple bonded carbon with two hydrogens. Like I think there are certain covalent certain ionic bonds that are a little bit weaker than that, but like generally speaking, ionic bonds are way stronger. Okay, so like that usually means what? They have way higher melting points. They have way higher what's called decomposition temperatures, which means like breaking apart the bond with energy. Why? Because it's a way stronger bond. To make those molecules pull apart, or to make those atoms pull apart, to make the molecules near them pull apart, way more energy. Way more energy. Because these are much stronger bonds, okay? And these happen pretty much exclusively between metals and non-metals. electrons. Okay. So, a classic example that's often given is if I had sodium chloride. So I'll give you the name, right? You've probably heard of this before. Sodium chloride. Okay, that's a name. Okay, that is a molecular name or a chemical name. You could, I guess chemical names are a little more common. And it tells you what? It says there's two elements, sodium and then this thing called chloride. And you're probably like, what is chloride? I've heard of chlorine. Is it the same thing? It's very different, but it's also very similar. And you're probably getting mad and saying, that doesn't make sense. Well, let me explain why. It ends in "ide," right? Oh, let's try that again. "Ide." And you say, sure. On the periodic table, we have an element called chlorine. It's right there, Cl. And if you look, take as much time as you want, there is no element called chloride. There's not. Okay, if you look at this, you're looking like, well, what about this? Oh, that's carbon. You're like, what about this? Oh, that's copper, right? I mean, there is no element called chloride. And you're probably saying, okay, so then it's chlorine, but why is the name changed? And the simple answer is because it tells us basically what's called oxidation state it's in, which is a fancy way of saying how many electrons has it either given up or how many electrons has it gained. In the case of "ide," it means it's gained electrons. Okay, it means it's the elemental form and it's gained its, how do I put this, easiest number of electrons to gain. Okay, so what does this mean? Fluorine is a halogen, right? Halogens all have 7 valence electrons. They really want to gain 1 electron, right? Think back to our example of fluorine. Fluorine bonded with itself because it really wants an electron, right? What's better than bonding with itself, though, would be like finding somebody like lithium or finding somebody like potassium who has 1 electron, who doesn't really want it. It's like a really good match, right? So the fluorine's like, I really want 1 electron. If it gets that 1 electron, its name changes because it's very different now. They're not the same thing. I mean, like, they're both fluorine, the atom, yes. Like, they both have 9 protons, yes. But now one has 10 electrons and the other one only has 9. If it has 9 electrons, it's fluorine, and it's insanely dangerous. I mean, like arguably the most dangerous thing in the periodic table. Like, you don't want to work with it. Okay, if it's F minus, it's still pretty dangerous, but it's substantially safer. Okay, like it's like, I don't know, like juggling knives versus juggling, I don't know, meat cleavers. Like, they're both dangerous. I guess you'd rather. Well, is that a good analogy? They're both pretty dangerous. Juggling knives versus juggling, like, tacks, I guess. Like, the knives are really dangerous. The tacks are like, oh, you might go, ow, I got myself, right? I guess. That analogy kind of makes sense, right? Fluoride, still pretty dangerous. And you might be saying, does this mean fluorine's bad, everything? It's the dose. As in any poison, it's how much you take. Okay, so, like, the toothpaste that you use probably has fluoride in it. Sodium fluoride, probably. Very small amount. If you look at your toothpaste tube, it probably says 0.24%. I think that's the percent. Am I right? I think that's right. Anyway, check. Very, very, very small percentage. But notice on the label, what does it say? It says, do not swallow the toothpaste. Okay? Little kids are not supposed to use fluoride toothpaste. They're not supposed to use it. Why? Number 1, they might swallow it. Number 2, they're smaller. And poisons, everything can be poisonous. That sounds weird, but pretty much anything can be poisonous. It's how much you take. Water, at a certain point, would become dangerous to you if you kept drinking it. Okay? It's a lot. Don't worry about it. You'd have to drink so much you'd be uncomfortable, probably saying, I'm going to stop drinking water now. Okay? But it can kill you. Okay? You eat salt on a steak, right? You put salt on it. And you're probably saying, well, yeah, I don't put too much salt. If you ate, like, the entire thing of salt in, like, a salt container, you would die, right? But you're not saying salt's poisonous necessarily. Okay, so fluoride is poisonous, but it's not. It's how much you're being exposed to. Okay, same thing in like drinking water, and that it gets kind of controversial. And I try to stay out of politics and teaching, but there's good and there's bad, truthfully. Okay, so now I'm going to get a bunch of comments saying I'm a shill for fluorine, or I'm a shill against fluorine, or I don't know. Good and bad to it, I guess. Right? Helps with your teeth a little bit. Igneous hydroxypatate is actually what your enamel's made out of. That's probably better, but that's a whole other conversation. So anyway, where was I at? Oh, yeah. We're talking about ionic bonds. We're talking about this idea of "ide." The "ide" means it's gained electrons, okay? And it depends on what element, right? So chlorine, so let's draw this out, right? We have our sodium. Sodium's a weird one. It's Na, It's the Latin word for it, which was natrium. Okay. If you ever go to the doctor and you're like muscles aren't working well, like imagine like you're like disoriented, and when you try to pick something up, like you grab too fast or your muscles are twitching, you might be diagnosed with something called hyponatremia. Hypo means low, like too low. Natremia, natrium, sodium, and then eum means like in the blood. So like hyponatremia is when you have too low sodium in blood, which can affect your muscles. Same thing with calcium. That's called hypocal. Oh, what is that? I don't know. It's been a while since I my biology in college talking about that. But anyway, so sodium Na with one valence electron, and then we have chlorine. Now it's just chlorine right now, and we'll see why. Right? He's got his 7. If I can get this to, if my mouse will behave. Geez, there we go. He has 7. Okay, and this is a great example of why Lewis dot diagrams are so nice, because you might be tempted right now. You might say, "Oh, it's gonna, a bond right here," and yeah, I mean that could make the chlorine happy, right? Sure, I agree with that. The problem is the sodium's not happy. The sodium's not going to want to gain an electron, and more to the point, even if he did, like even if this was what his plan was, he can't get more than one from the chlorine. The chlorine's not going to share more with him. I mean, so the point is you say, oh, it's not covalent, right? You say it's a metal and a nonmetal. It's going to be ionic, which means what happens? The chlorine basically reaches out and says, give me, just like any other covalent bond. It starts with like both sides reaching out essentially and trying to grab the electrons, right? Except in this case, sodium is not interested in gaining. So he's really not reaching out for chlorine at all, right? Technically, there's a little bit. Very small amount. But the chlorine's way more aggressive. He just goes yoink, and he's able to pull it away. The real reason for this is because, number one, chlorine has high electronegativity, and sodium has pretty low ionization energy. Remember, ionization energy is the idea, if you don't remember this, that a molecule can lose an electron, and it's how hard does it fight to stop it. Okay, it always takes energy to take an electron, but sodium is like pretty weak. I guess take it. Chlorine would fight you. You're not taking my electrons, right? So anyway, what happens? It's called an ionic bond because guess what we just made? We made 2 ions. And you say, prove it to me. So let's prove it. So the sodium has given up his valence electron, and he now has a charge. He still has 11 protons, right? If he didn't have 11 protons, he wouldn't be sodium anymore, would he? So he still has 11 protons, but now he only has 10 electrons. So he has a surplus of charge, or a surplus of protons, if that makes sense. And we can't change that, right? That's not on the table. The only thing we can change is electrons. He lost an electron, which means now he has 11 positives and only 10 negatives, which means he has a charge of +1. Okay, and again, my mouse is not really cooperating. Let's try that again. There we go. A +1 charge. You could put a 1 in front of it, like +1. It's not usually done. Okay, just a plus sign. If you really want to, I guess you can, but I'd recommend against it. Okay, and then chlorine, meanwhile, I guess I'll change colors again. He is now chloride. Why is he chloride? Because he now has 8 valence electrons. Okay, he has 8. So now he has 17 protons. He's always had 17 protons. Chlorine has an atomic number of 17. He did have 17 electrons, and now he has 18. So he has a surplus of negativity, which means he has a negative, if my mouse will behave, a -1 charge, which again is usually just drawn as a minus sign. Okay. So you say, oh, they're both ions now. Ions are an element with a different number of electrons. Simply that. Okay, we have 2 kinds. We have what's called a cation. I guess I'll put this in the notes. I probably should put this here because you're probably like, oh, I'm going to take notes on this. We have 2 kinds of ions. Look at that's even different color. We have what are called cations. Oops, I guess I'll do it right here. Cations and what are called anions. Okay, cations are simply positively charged. Oops, I can't spell. Positively? Yeah, that's right. Positively charged. Okay, oops, let me, I guess, stretch this out a little bit. And anions are negatively charged. Okay, let me move this up a little bit. There we go, perfect. All right, so cations and anions. Okay, so cation would be your sodium. Your anion in this case would be chloride. And notice I'm stressing the word chloride because there's differences. If I said chlorate or chlorite, that's different. It's not Cl anymore. It has Cl in it, but it's not just Cl. Chloride, if it ends in ide, you should immediately think, oh, it's the anionic form of chlorine, which is Cl minus 1. Okay? If you're saying, of course you think it's easy, you teach chemistry. I mean, I guess, but I also think it's just seeing it a bunch of times and making it click. Okay? So just for the sake of like trying to say don't worry too much about this, don't panic about the names, is just let's take a look at the periodic table and you tell me where it gets, I don't mean to sound, that sounds kind of angry. I mean like, hopefully I can make you feel not as scared, I guess is what I'll say. Instead of saying you tell me where it's hard. You pick an element. Ides are all going to be over here. We're not going to have any of these guys be ides because they can't be ionic anions. They can't be anions, basically. Okay? Only these guys. Okay, any element I pick. So like carbon becomes carbide. Oxygen becomes oxide. Fluorine becomes fluoride. Selenium, selenide. Bromine, bromide. Hopefully you're like, oh, I got it. It's not that hard. Phosphorus is phosphide. Silicon would be silicide. That's kind of rare, but it is what it is. Nitrogen is nitride. Okay, so hopefully you're like, oh, okay, it's not that bad, because it isn't. Okay, it can get a lot worse when you get to what are called polyatomic anions, which if you're a junior taking chemistry, you will talk about those. And if you're a freshman taking physical science, you will not talk about it this year, but you'll talk about it when you take chemistry. So look at that. Anyway, so let's finish off with, because this video is probably getting a little long, let's finish off with ionic compounds. I'm going to delete all this, I suppose, just so I can have a fresh thing. Of course, you can pause it, right, if you need to, like, or rewind, I guess, now. But you get the point, okay, if you need to see that. With ionic compounds, it can get a little bit tougher, but it's never that bad. So, for example, if I gave you the name, I don't know, calcium fluoride. Why not? What you do with this information, you say, how am I supposed to do this? I want to find the formula. This is the name, and I want to find the formula. The formula is like what makes up the molecule. So if we go back to salt, NaCl, it's NaCl. Sodium chloride, 1 sodium, 1 chlorine, NaCl. Okay? Calcium fluoride, of course, is going to be different. What you want to do, what I would do, is write out the symbols first. So for calcium, you look at your periodic table, you say, where's calcium? Calcium, oh, here it is, Ca. And you look at it, oh my God, that's terrible. Let's try that again. Here we go, Ca. Okay, this mouse, I need to get this drawing tablet because this mouse is going to make me go crazy. Like, I can't get it to go up. It ain't working, man. Oh, is it because the battery almost fell out? Let's try that again. Maybe that's why it was misbehaving. I don't know. There we go. Maybe it's better. Yeah, that's acceptable, I suppose. I don't know. And calcium has how many valence electrons? He's got 2. Okay, so how do I know that? He's an alkaline earth metal. He's in the second group. He has 2. Okay. And then we have fluorine. Fluorine has 7. He's a halogen. Every halogen has 7. They're hungry. Oh, let's try that again. That looks terrible. 7 valence electrons. And again, if you're tempted to say, well, could it be a covalent? No, it's a metal and a non-metal, especially with fluorine. Fluorine is going to dominate this big time. So what happens? Fluorine says, I'd like an electron. I'm going to take it. He reaches out. What does he do? He says, this one. And it does not matter which one you pick first, by the way. He says, gimme. So he takes it. And when this happens, fluorine is now a happy camper. Okay? So if you think about it, fluorine now has gained an electron. He now has 8 valence electrons, right? And he has gained a charge. He is now fluoride. He has a -1 charge, which, yes, makes a big difference. Okay, calcium, meanwhile, what has happened to him? Here's your calcium. He still has 1 valence electron left over. And technically, he would have a +1 charge. Okay, and this is not stable. Calcium will not stand for this. He's not going to let this happen. But thankfully for calcium, there's plenty of fluorines to go around. When you do these problems, you basically make the assumption that you're always going to have enough of whatever the ingredients are. okay? It's like if I told you making a sandwich takes 2 pieces of bread, and I say, can you make me 10 sandwiches? The assumption is you're going to have 20 pieces of bread, right? You need 2 for each one. There's 10, so you need 20, right? If I said there's 15 pieces of cheese, the assumption is you can get that cheese. Does that make sense? So when you make these, when you're doing these problems, don't think like, oh, but do I have enough calcium? The assumption is yes, you will. Okay, you're never going to run out when you're forming compounds, if that makes sense. Okay, so you say, how do I fix this? Well, I have an extra electron. Somebody needs to take it. Who's going to take it? Fluorine's happy. He's not going to take it. So along comes another fluorine, right? And he also has 7 valence electrons, right? He's fluorine, right? He does not have his 8th yet. But he spots this electron and he says, gimme. So he takes it. And now what do I have? I'm going to block this off so it's a little bit easier to see. The calcium now has given up 2 electrons. He's a cation because he's positive. You say it's positive. He's given up 2 though, which means he has not just a plus charge, he has a plus 2 charge. Okay, very important. A plus 2. Meanwhile, fluorine, we have 2 fluorides now. We have, again, this guy here with his 8 valence electrons, and he has a -1 charge. We have a second fluorine, right? We needed 2. So we have a second fluorine. Here he is. 1, 2, 3, 4, 5, 6, 7, 8 with his -1 charge. And you might say, oh, there are 2 negative ones, and there's a positive 2. Hey, those cancel out. Exactly. And that's what gives us the molecule. This molecule is called calcium fluoride, and its formula, like if I looked on a bottle in a chemistry lab and I was like, I need calcium fluoride. I don't know why I need calcium fluoride, but yeah, let's just say I need calcium fluoride. It would have this formula, okay? CaF2. And this information tells me what? A calcium. How many calciums? There's no number. You say there's no number. It's assumed to be 1. It's like having x in algebra. If it's x plus 5, the assumption is it's 1x plus 5, right? The coefficient would be 1. In this case, the assumption is it's 1. The subscript, so I'll put this, I guess, in, I don't know, put this in green. Why not? Okay, this number here is called a subscript. And that subscript tells you, how many of that element. And I'll just leave it at that for now, because you can also tell you other things. But for now, we'll leave it at that. Okay, how many of that element in that molecule? So one molecule of calcium fluoride has 1 calcium, and it has 2 fluorines. Notice I'm like showing it on other sides. Remember, these things have charge still. Just because they're combined and the overall molecule is neutral does not mean it does not have areas that are like, hey, more negative. They're surrounding the positive. Okay, very important, right? Ionic compounds are very strong for that reason. It's also why they interact with other molecules. They have very strong intermolecular forces. Very, very strong, okay? So what it simply means is this. The molecule has formed, it's always going to have 3 atoms, 1 calcium in the middle, and then 2 fluorines on the sides, if that makes sense. It could be the top and the bottom, but you could rotate it and think of the side. Does that make sense? Okay, so that's calcium fluoride. And maybe you're like, oh, cool, that's not that bad. Okay, it can get a little bit tougher. So we'll do maybe one more and then we'll probably call this video quits. Just a lot of information. I don't want to make these videos not terribly long. I'm already kind of dreading to see how long this video is, because I kind of went in thinking I was going to make a 20-minute long video, and I think it's probably now more like a 40-minute long video. But that's okay. I guess put it on fast speed maybe. Oh yeah. So let's try maybe a slightly harder one. What if I gave you magnesium nitride? I don't know, pretty classic one. So magnesium nitride, for this one, we look at it and say, okay, let's get our symbols. Be very careful. Every year that I teach chemistry, that I teach anything with chemistry, be careful. Magnesium is not the same thing as manganese. They're different. Manganese is Mn. That's a transition metal. Magnesium is an alkaline earth metal, I should say. Okay, magnesium is very different than manganese. They are very, very, very different. And they have similar symbols. Magnesium, think of it as like there's a G sound. Magnesium is Mg. Manganese, I don't know, hopefully that helps. Okay, is Mn. So magnesium is Mg. Be very careful. Okay, and Mg, it's an alkaline earth metal. Oh my lord, there we go. That's hard. Let's try that again. There we go. Oh my, I can't draw today apparently. Mg, there we go. Has 2 valence electrons, just like calcium, right? It's an alkaline earth metal. Nitride, hey, it ends in ide. This is nitrogen, okay? Nitrogen with what charge? It'll be a -3. And you say, how do you know that? Well, I memorize a lot of stuff, but it's also, you can figure it out. If you look at it, you're like, here's my nitrogen. He has 5 valence electrons, okay? This is a metal and a non-metal. It's going to be an ionic compound, okay? And what happens? You say, I know, nitrogen is going to take them. Yeah, he is. The problem is what? He says, give me this electron. He says, give me this electron, right? He wants both, right? And, hey, that's great for magnesium. He has sold his wares. He's happy. He returns from market and says, I did a good job. Nitrogen's very close. He wants one more. But magnesium's going to slap his hand away and say, you're not taking one more of mine. It's 2 or nothing. I'm not giving up just 1, and I'm not giving up 3. It's 2 or nothing. And so magnesium's happy, nitrogen's kind of mad. But guess what happens? Another magnesium to the rescue, right? So here comes another magnesium. Says, oh, electrons, I got those. I can sell mine. Yeah, I cannot draw this. It's the mouse is just not behaving, man. It ain't behaving. Notice I'm being pretty meticulous about making sure it's capital M, lowercase g. That's very important. You have to make sure for an element, if it has 2 letters, you better make sure it's capital lowercase. And yes, it does matter. It's not just me being particular. It's very important. So here comes the magnesium. He says, I got 2. And then the nitrogen says, great, give me 1. Now, to make things simple, right, what's going to happen in the case of this thought process is that the magnesium will say, okay, take this 1, but I want somebody else to take the other one. And then who's going to take it? The nitrogen's happy, so along comes another nitrogen. And that nitrogen says, okay, I'll take, I want 3, right, because he starts out with 5. And this magnesium says, I only have 1. And you can probably like, oh my God, is it ever going to end? Is it ever going to end? And yes, it will end. You'll see in a second it's about to end. The magnesium says, okay, take 1 of mine. He's happy now. This nitrogen is like, no. I want 2 more. And then lastly, 1 more magnesium says, did somebody say, oops. This magnesium says, did somebody say 2 electrons? And the nitrogen's like, yes. So what happens? Hey, we can finish this off because we have these 2 electrons going to this nitrogen. And now everybody's happy. Hopefully you can look at this and say, okay, I see it. Everybody's happy. And maybe you're saying, oh, I know the answer. I know it's going to be Mg3N2. And you're correct. But to prove a point to you, right, just to make you understand what's happening here, think of it as the cation side and the anion side. The positive side, the negative side. How many positives do we have? We have 3 magnesiums. So I have magnesium. And what charge does he have? He has a plus, oops, if the mouse will behave, a plus 2. And then we got, you know what? Actually, I'm going to be ready for this. I'm going to be fancy. Fancy pants. I don't know if it's going to be worth it. Let's see. Oops. Did that work? See, now I'm trying to be fancy, and it's not even going to work, is it? That would be tragic. Yeah, I should be able to copy that. No, I want to copy it. Let me copy it. I don't think it's going to let me copy it, is it? See, I try to be fancy, and then, of course, it doesn't want to work. Oh, there it goes. Okay, I guess it just took, more. Let's try that again. There we go. Okay, I guess it's maybe worth it. I don't know. At this point, maybe not, but that's fine. So we have 3 of these, right? Because we needed 3. And I want you to think, oh, you're probably going to make me think that we should add these together. The positive sides, they sum to positive 6. So then I can do the same on the anion side. We have 2 nitrogens. So for my nitrogen, I have, and these are now nitrides. I should be technical, right? These are nitrides. They have a -3. And you're like, -3? They gain 3 electrons, right? So I have 2 of these -3s. Okay, and to be technical, I should include the extra electrons. Okay. It's kind of messy, though, with the way this mouse is working, but, And you say, oh, 2 -3s, that's -6. And you're like, oh, these cancel out. And that's exactly how it works, which means your answer would indeed be Mg3, oops, N2. Make that look a little bit neater, hopefully. N2, okay? That's magnesium nitride. 3 magnesiums, 2 nitrogens. And if you're asking, well, how does that work? Like, what do they look like? We're getting into what's called solid state chemistry. We're starting to get into like how crystals form, basically. The short answer is you want to have it where those 3 positives are not next to each other. They're kind of like interspaced between the negatives. So you want to kind of like make it where the negative charge is distributed in a way where the positives can be near it while not near each other, if that kind of makes sense. That's not for this class, though. That's like college level chemistry, okay? Yeah, we don't want to talk about lattice numbers and coordination numbers and other stuff that can get hard. Yeah, you don't want to do that for high school. At least not unless it's like AP. And even then, I don't even know if you do it in AP chemistry. So anyway. Okay, so hopefully you're saying, oh, that's not bad, right? There's a shortcut you can do. I'll show you the shortcut quick, and then we'll probably call it quits. The shortcut, so let's do a new page, right? The shortcut is going to be, if I give you something, so if I say, I don't know, calcium oxide. Or actually, well, let me do that one next. There's a reason. Let's get that one over. Calcium bromide. Sure. Okay. You are more than welcome to do it the old-fashioned way, the long way. Nothing wrong with that, right? But if you're like, is there a faster way? The answer is yes. So we can take calcium. And instead of drawing the electrons, we can just say, hey, we know it's going to have a +2 charge. It's always going to have a +2 charge. It's not going to have a +1 state. It's going to be +2. So you say it's +2. I know that. And then you look at bromide. So you first look at bromine, Br, and you say, oh, bromine is a halogen. It's in group 17. It has 7 valence electrons. He's going to want to gain 1. Well, if he gains 1, his charge is -1. Okay? So this kind of makes sense? And then what you do is simply take the numbers. And when I say numbers, I'm be very careful here. Take the positive one here. You say, but wait a second, it's negative. I know it's negative, but the number is what I'm moving down, not the sign. Okay? I don't care that it's negative for this purpose. The charge is no longer going to matter when we do this, if that makes sense. Okay? So I put, computer's yelling at me. I put that the 1 there, the positive 1 there, and then I take this 2 and bring it down. You're probably like, oh my God, it's getting messy. Well, what have I just made? I have Ca with a 1, which we just leave as Ca. And then I have Br, and how many bromines or bromides? 2. CaBr2. And that's your answer. And you're probably like, wow, that's a lot faster. Does it always work? And the answer is it does. Be careful, because there's one way you can get jammed up. So I'll show it to you real quick. So I think I gave you, calcium oxide last time, right? So I'll do that. Calcium oxide. Okay. And you say, okay, I'll do the shortcut, right? Because that's faster, right? That's smart. So you say, hey, calcium we know is Ca. We know it's got a +2 charge. And then you say oxide. Okay, that's oxygen. He has 6 valence electrons, which means he will have a charge of -2. And you say, oh, crisscross, right? Take the 2, bring it down, take the 2, bring it down. So you say, oh, take that 2, bring it here, take this 2, bring it here. And you would get an answer. You would get Ca 2O2. And you're like, I'm done. And unfortunately, you're not done, because this would be wrong. And you're probably going, how dare you? You told me it'll always work. It does, but you have to make sure the subscripts, and this is only for ionic compounds, mind you, have to be non-reducible. And 2 and 2 can be reduced. They have a common factor. Their common factor is 2. You can divide these both by 2. And if you do that, what do you get? You get simply CaO, which is calcium oxide. Okay, it works if you're like, but wait, crisscross. Yeah, crisscross still works. You just have to simplify